All right, recording, it's rolling. It's Wednesday, March 22nd. So I'm going to do some Unit 5 momentum review with you guys. Have some paper out, have some notes out, because I'll set up some problems with you guys and then see if you guys can finish them, solve them. Got some problems picked from the book, but we're going to start with some PowerPoint slides. Got some FRQs lined up for the next couple of days. AP Classroom, hopped in there, saw that a couple of guys have already started on that. So we're going to go over those on Monday, right? So Unit 5, multiple choice questions, Part B. Okay. Okay. And then I'll have a quiz written for you guys by Tuesday. Okay. That'll be an in-class quiz then. Okay. So you guys got that so far? All right. Another thing we did yesterday were these course selection forms. So there's the version if you're 10th grade going into 11th, and I've got a couple of guys, right? You have a pink page that says 11th grade because you're going into 11th. Right? If you're 11th going into 12th, then you have a green page that says 12th because you'll be going into 12th. There are also some seniors. If you're a senior, don't worry about this at all. Right? So so it's going through the day yesterday. So there's teacher initials apparently. So I think I might have to sign this for you guys under science. So just whatever science class you want to pick. Go ahead. And does anybody have any questions about this otherwise? Course selections, right? Anyway, if you think you want a signature from me, if you just have this page out, then at some point in class, because I'll be walking around checking you guys' work for momentum as we're going through that review. So have this page out, and if you want a signature, then I'll sign under science. So I might help you down the line. All right. So, all right, momentum review. Switch my screen over here. All right. Yeah, so yesterday you guys were putting these posters together. So let's look at the slides that were specifically for momentum. Okay. So you guys remember momentum is mass times velocity. Okay. This is a vector value, so directions matter, right? Now that's in contrast to things like energy, for example. Like if something's in motion, has mass and has a velocity, you could also say it has some amount of kinetic energy, right? That could be 1/2 mv squared would be kinetic energy. Okay. So you can quantify that too. It's the same ingredients, right? Mass and velocity, right? But with kinetic energy, you don't really care about direction. So it doesn't matter if it's going up or to the right or down, right? It's just some value in joules of kinetic energy. But momentum and kilogram meter per second, right? Well, that matters if it's going to the right or going to the left. So you guys know this is involved in collisions, right? And the fact that momentum is conserved and it's a vector quantity, well, suppose you got two objects colliding. Well, are they doing head-on collision, like one's going to the right, one's going to the left? Because in that case, the momentum would subtract from it. It would subtract. Versus if they're heading the same direction, like maybe like a fender bender collision, right, where one car is going slow and the other car is coming fast up behind it, bam, they slam that way. Well, in that case, maybe the momentums would add because they're both in the same direction. Okay? Now you can't take this to 2 dimensions. AP doesn't really focus on that. AP just pretty much focuses on just 1 dimension at a time. But okay. All right. Closed system, open system. We've had different perspectives on this, but I want you guys to write down on the paper that you have in front of you, since you guys have your notes out. What would this look like in terms of momentum specifically? What would make a closed system versus an open system? Ooh, paper for it has paper here. All right. All right, everybody got paper, something to write on? Okay, so if you don't, I put some paper right here. That's paper over here. Everybody needs paper. All right. So for a closed system, in terms of momentum, did you guys say that right there? The sum of momentum initial equals the sum of momentum final. Okay. And we say initial and final, you're talking before what and after what? The collision. Yeah, collision. Right. So whenever you see a collision, the first thing you should think is something to do with momentum. Every once in a while, there's a curveball and they ask something that's not related, but if you see the word collision or some scenario involving collision, probably do this, right? Right. So what would make a system open in this context? How about if there's an impulse, right? Right? Plus or minus a change in momentum. That's what impulse is, right? Change in momentum. Okay. And it's sometimes too, you can put little vector arrows above the P to indicate that these are vector quantities, right? So if it's going to the right or going to the left, right? Or forward or backwards, that makes sense. Okay? Right. And the plus or minus could be, well, is there momentum entering or leaving the system, right? Is there a force acting on the system, or is, right? So which way is momentum going? Right. Closed and open systems in other contexts, you might say, like from an energy context, you might say sum of energy initial equals sum of energy final for a closed system, or the initial energy plus or minus the work done is equal to the final energy of that system for an open system, right? Something like that. And the other perspective on closed or open systems is there a net external force, right? Is there some kind of net external force? Okay. Right, so you guys good with the closed open systems? Okay. All right, conservation of momentum. All right, oh, there's a classic collision right there. Let's see if you guys can write just basic, just for what you guys looking at right there, just in one dimension, along one axis, two objects collide. So for that system, can you guys write the equation that would correspond to that setup? Okay, I'll look around, see how you guys are doing, and also assign any of those green and pink pages. You guys have that. All right. So did you guys say that right? You guys said that right there, right? Right. So mass times velocity plus mass times velocity equals mass times velocity plus mass times velocity, right? Got mass A and B, right? And then before, and then after the collision. Right? This guy said that. Right? I mean, you're gonna have to use that to pick up some points in the AP exam. There's no way that doesn't come up at some point, right? Right? You guys do this? Okay. Is everybody good on that? Right. So you guys could like know that by heart, right? That's like scripted in your brain by this point in the year. Next one.
At this time, teachers, please check your list of students who are supposed to be in that SAT makeup. We only have about 50% of the students in the gym right now, so please double check that list and send all those students to the gym. Thank you so much for your assistance.
All right. Do that. Just double check this while you guys are okay. So for perfectly inelastic, go ahead and do that. Let's make sure I don't see any guys here. Nah, you guys good. All right, perfectly inelastic. Okay. So it starts out the same way as just the general conservation of momentum, right? We've got mass times velocity for each one, right? But now they're just going to, my screen's frozen. Okay, hang on. Time out here. Let me pause this recording. All right. Is my screen sharing? Okay, I think the screen's sharing. I think this is working. Okay. All right. So what? Right. So you guys came up with that, right? Right. So they'll combine and make one giant mass, carry a common final velocity, just like that, right? That's AP's favorite type of collision to ask about, right? Perfectly inelastic. Right? Speaking of these terms, perfectly inelastic versus elastic. Right? The way that AP goes with the terminology, right? If they say elastic, they mean perfectly elastic. That's what I would say. Perfectly elastic. They just say elastic. If AP says inelastic, they might be referring to two objects colliding stick, perfectly inelastic. or they might be just referring to just not elastic. Right? So the word inelastic could just be just any general collision. Okay, that's not perfectly elastic. Right? So if it is perfectly elastic, okay, here's what you would. Here's the important things to know. Right, one is that momentum is conserved, but that's true for any kind of collision, so that doesn't really help narrow it down. Okay, but the important thing that makes a collision perfectly elastic, or AP would just say elastic, okay, is that kinetic energy is also conserved. Right, so that's your 1/2 mv squared bits before and after the collision. Right, it all has to equate. Right, so all the energy stays kinetic. Oh yeah. Last slide. Okay. Okay. There. Yeah, so you guys remember too, this presentation is, I posted it to Google Classroom, I think back in November, December. It was back when we were doing a midterm review. Okay. So, yeah.
So you said when they talk about perfectly elastic, they just mean elastic. When they talk about elastic, they mean perfectly elastic.
Yeah, if AP ever just says elastic collision, they mean like perfectly elastic, where everything on this screen is true. If AP says inelastic, it may not necessarily be perfectly inelastic. It just means that at least some energy goes from kinetic to like maybe like thermal or permanent deformation, something like that. Okay.
So it does not.
Yeah, not necessarily. Yeah, you can't assume. Yeah. So if they say inelastic, they don't necessarily stick together. Okay. Right. But they might. Okay. All right. So if you guys go to college and take physics, there's a good chance that you'll have to be able to take that system of equations in green and come up with what's there in yellow. Now that takes a lot of time and a lot of paper to go from the green to the yellow. Okay, so it's good to have this in your back pocket for college, especially. Now for AP, they usually ask what you guys have seen like a number of questions. Usually a good thing to know is this conservation of kinetic energy. Again, that's only for elastic. You can run that check. Usually I'll ask some kind of multiple choice question where you can narrow it down based on that. Or it might be something that's straightforward enough where you can figure out, like, for example, this Newton's cradle. Right? This is really close to modeling an elastic collision, right? Right. So they might have, I've seen them asked before, where they just have like one object at rest and another object like slams into it, and they're equal mass. Now, if they're equal mass and one starts at rest, then wouldn't it make sense that one just transfers all the momentum to the other object, like you just saw right there? Bam, it's complete transfer. Okay, so I've seen them ask that too, but they would not expect you to be able to come up with the yellow all by yourself or memorize that. They don't expect that. Okay, okay, so you guys hear that? And so they, all right. All right, coefficient restitution. This is not on the AP exam, but just extra stuff I want you guys to know. This is a way you can quantify how bouncy is something, right? So if you have like a spectrum, on one end is perfectly inelastic, on the other end is perfectly elastic. Well, in the real world, like collision is somewhere in between. You drop a tennis ball and it bounces up halfway or something like that, right? So if you look at the pre-collision difference in velocities compared to the post-collision difference in velocities, right? So take the ratio post over pre, right? You can quantify coefficient restitution, right? And just make it a positive value, right? That's what the absolute value is about. Okay. Right. Now, here's maybe something they could ask, even though coefficient restitution not really on the AP exam, but I could see them maybe asking something like this, like for FRQ. They could give that to you. They could say, here's what coefficient restitution is. It's the rebound speed compared to the crash speed. Right? No, this is a modified version. This is if one of your objects is the Earth, right? So the Earth is basically not going to move, right? So you're bouncing an object off the floor. Right? You guys did this as one of your labs. You guys remember this one of your labs, right? And they say, say you drop it from 100 centimeters and it bounces up to 70 centimeters, right? Right? Can you figure out what's the coefficient restitution? Right? Now, I'm giving you kind of a head start here because you would have to figure out these top bits, right? That the crash speed would be square root GGH, but you guys have seen that so many times from conservation of energy, right? And we've done this like what, at least like 20 times, right? That the crash speed and the rebound speed would be square root GGH, some version of that, right? So the drop height is capital H and the rebound height is lowercase h, right? So can you put 2 and 2 together and figure out what is the coefficient restitution just based on the drop in the rebound heights? Can you guys figure that out? Okay. See if you can on your paper, right? Because that should be something you should be able to do. So AP says, here's what coefficient restitution is. Here's the drop height. Here's the rebound height. can you figure out what is coefficient of restitution? Now that we've given you the definition of this thing. All right, yeah, winner right here. All right, so yeah, I think you guys figured this out, right? So you just take the ratio of this square root 2gh over that square root 2gh. It's the same g, so the 2 and the g cancel. Right? It's just the square root of the ratio of the heights. Right? Right? Tells you like how bouncy it is. Okay. You guys get that? All right. Ooh, impulse. Right. I mean, you're gonna get these questions, right? AP loves graphs. You're gonna get force versus time graphs. Whenever you see a force versus time graph, you're thinking in terms of momentum, right? Momentum, impulse, change of momentum, right? That's what impulse is, right? Change of momentum, right? So we're talking about open systems, right? This could be an open system that's like just this apple or just a baseball, right? You're looking at its mass and its velocity, and then it's hit by a bat. Bam! That's an external force. Open system, right? They go hand in hand, right? External force and open system. Okay. Can you guys write the impulse equation? And there's so I could say delta P equals, and there's like two perspectives on this. Okay. See if you guys remember what those two perspectives are. Impulse, change of momentum. That sounds right. All right. Anybody's got a paper signing this time? All right. Yeah, that's it. That's it. All right. All right. So you guys came up with, okay, so impulse, change of momentum. Okay, that could be mass times change of velocity. And it's caused by a force times the time interval. Okay. Oh, and really it's an average force. If you have a variable force, we care about the average force, right? Right. Either that or it could be a constant force. So if you're looking on this graph, a lot of times these are variable force graphs. So it'd be like the area of this triangle. But if this was like an iceberg, you let the ice melt, it would melt down to this dashed line level, right? And then create this rectangle shape, which has the exact same area, right? So it's the exact same impulse, right? You guys get that? Okay. Right. I guess the other thing I could say about this is, right, mass times change velocity. That's if you have like a point mass, it's a constant mass. You could actually modify this in a weird way. So what if you had like a conveyor belt and something was dropped onto the conveyor belt? So it was always changing the mass, right? But you want to keep the conveyor belt going at like a constant speed. Well, you have to like keep increasing the force, right? So this could be like a change of mass times some constant velocity, right? You could change that below. I don't know. I've never seen AP ask that, but you know, just stretch your imagination a little bit. Yeah. All right. Ooh, ballistic pendulum. Um, here's a good one to be able to put together. Now, this is a complex question, right? Because there's multiple parts to this. Here's what I want you guys to figure out. And I've set up the framework for, I mean, all you have to do is like pop, 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 pop. It's set up for you to solve, just following this green box followed by this yellow box. Okay? If you know the mass of the bullet and the mass of this block that it's being fired into, and you also know the length of the pendulum, and you also know the starting angle, so you know all those things, and you also know this height change, right? So you know how high it swings up to, right? Can you calculate the firing speed of the bullet? Okay. Actually, there's a little bit redundant information, because if you know L and you know theta, you can find out what H is, right? Or if you know what H is and you know what L is, you can find theta, right? So at least figure something out, right? So either figure it out in terms of L and theta or figure it out in terms of H. Can you solve for the firing speed of the bullet? And you know everything else there. Right? Can you solve for the firing speed of the bullet? Give you guys a minute to do that. This might be like a practical way to figure this out. Suppose it's like the year 1880, right? And nobody has radar guns or speed gates. It's like, hey, I wonder how fast this gun can fire. I can figure out, oh, you set this up, and this would be an actual way that you could actually do this and get a pretty accurate answer. This would make a really good FRQ question too. It would be pretty indicative. If you knew physics real well, you'd solve this. All right, start going down the line here. All right, so remember you saw this like backwards in time in terms of what happened, because what you're solving for is the first thing that happened was the bullet was fired at some speed. Okay? The last thing that's happened is it swings up to some height. So we start with the last thing. Say, okay, well, if it swings up some height, I can use conservation of energy. Say there's some kind of 1/2 mv squared that turns into mgh. Now the mass we're talking about is the bullet plus block that's all embedded together, right? The bullet's embedded in the block. Okay? So that's going to cancel out anyway. And oh, look at that. Speed equals square root 2gh. I mean, you guys just saw that a couple slides ago anyway, right? Like ball bounce off the floor. I mean, you guys see this all over the place. Galileo drops the ball off the tower. How fast does it crash? Square root 2gh. Okay? Right. So however high it swings up to, whatever that height is, right, is going to be related to how fast, like post collision, the bullet and block together get going in motion, right? And that's the relationship, right? Is that true? Now, you may have gone the extra step and said that this height is equal to L times 1 minus cosine theta, right? Just do some geometry, right? Because here, this length is equal to this length, right? And if you scoot straight over, right, wouldn't this height be L minus L cosine theta? Because this leg of the triangle would be L cosine theta, right? So this height is L minus L cosine theta, and you can factor the L out, right? Right, so here's the conservation of momentum. Right, so all the momentum came from the bullet in motion. Right, then it bam slams into the block, and that creates a perfectly inelastic collision. Right? Now you really care about what is the speed of the bullet, so we're going to substitute out the speed of the bullet block going together. It's going to go like that. Right. Do you guys want to see the geometry of how to substitute out the height? Yeah, okay, let me do that. Let me switch over here. So what's down here swings up here. Okay? And you know the height change. That's like h. Right? What's that height equal to in terms of this L, which is that L, and this theta? Okay? Well, I can make a triangle here, make a right triangle. I can say that, well, this whole thing is L. So this part from here to here must be L times cosine theta, right? Guess that? If this whole thing is L, then this must be L cosine theta, right? Because I have a right triangle right here. Right? You guys see that? Okay. And then, yeah, if this whole thing is L and this is L cosine theta, then the difference here to here, which is the same thing, right? Top of the block to the top of the block, or the bottom of the block to the bottom of the block. Right? It's the same height change, right? So this is also h, right? Okay. Well, that must be L minus L cosine theta, right? And then if you like, you can factor an L out. Right? So you can do that too. Right? Should be able to do that, right? We've done it a bunch of times. Right? Good skill to have right there. All right. Oh, yeah.
On the other slide.
Back to the presentation here. All right, so back over here. Yeah.
Could you explain why on the energy conservation part,
Yeah.
for the kinetic energy part, you have both masses instead of just the bullet?
Yeah, because this is a post collision, right? So the collision happens, and then we're gonna kick off this conservation of energy. Yeah, so the bullet's embedded in the block. Yeah, yeah,
Okay.
yeah. Okay. All right, so you guys get there? Over that? All right, yeah, so good thing to be able to do that one right there. All right, 2 dimensions. So maybe you're playing billiards and you strike the cue ball, it hits this ball and corner pocket, right? So you take off different directions. 2D plane. Okay. Right. So again, AP doesn't really focus on 2D collision, so you almost certainly wouldn't see anything like this. But here's how you would do it in principle: okay, is that the momentum in the x direction is conserved and the momentum is in the y direction is also conserved. Okay. So if you had like a ball just sitting here at rest, like this green ball just sitting at rest, and this red ball comes in, just only along the x-axis. What I do know is that after this collision, bam, the momentum strictly upward and the momentum strictly downward have to cancel out, right? Because there was 0 momentum in the y direction to start with. The example. Okay. Right. Center of mass. Okay, so this kind of spans a different units. You think like momentum or rotational dynamics or kinematic motion. Okay? So you can take like a weighted average of masses, right? So it would look something like this. Right? So for these 2 objects, what's the center mass between these 2? Maybe possibly they might be connected by a light rod, and you're trying to balance it at a point. Where's that point balance? Oh, the balance like right there. Right? So mass times position plus mass times position divided by the sum of masses gives you like the average position. Okay? Now, in AP question about center masses, what they really like to ask is something like if there's a collision, if you're focused on the center mass, like what happens to the center mass, right? So maybe like this object collides with this object or something, right? And the center of the masses of between the 2 objects is moving at some speed. Well, after the collision, it keeps doing exactly what it was doing before the collision. So if you only focus on the center mass between 2 objects, you would never know when the collision happens. Okay? If you take that to heart, if you know that fact, that'll pick you up some points on the AP exam, right? That if you're only focused on the center mass between 2 objects that might be in motion, even relative to each other, okay? Just by focusing on that center mass, you would never know when the collision happens between those 2 objects because it just keeps on doing whatever it's doing. Okay. Okay. Let's go that. All right. So I think that's going to cover, yeah, because after this just goes into rotational dynamics. Okay. So any questions so far about momentum? Okay. I think we hit all the big points that you could be asked about on the AP exam. Okay. So I've got some college physics questions lined up. So back to the old textbook. Right. So textbook is organized. There's these warm-up questions, and there's some conceptual questions, and then there's the main problems. So I'll pick 1 or 2 from each section. Okay. So warm-up. Looks like I was looking at number 6 and 7. Right, number 6. Zoom in here. We got an astronaut with a mass of 85 kilograms. Right, including her suit, stands on a wait, what? This is okay. Standing on a spherical satellite, mass 375 kilograms, both at rest relative to nearby space station. Okay. She jumps at a speed of 2.56 meters per second directly away from the satellite, as measured by an observer in the station. At what speed does the observer measure the satellite traveling in the opposite direction? Okay, so we got this third-party observer watching. We got the astronaut, and the satellite. Right? Okay, so there's like 3 objects going on. Okay, we got this big old station here. Okay, now maybe the station's in orbit around the planet or something, but we're just going to treat it being like from this frame of reference, right? Right, and then we got an astronaut and a satellite, right? So an astronaut out here and a satellite. Maybe I'll just do like a ball satellite. How about that? Like something like that. Okay. And they're gonna push away from each other. Okay. So 85 kilograms for the astronaut and 375 kilograms for this satellite right here. Okay. Right. Right. And then the astronaut's going to jump away at 2.56 meters per second. Okay. And the question is, how fast is the satellite go? I call it V sub S, that speed of satellite. Okay. You guys see that? And so I guess what you should be able to take that paragraph right there with those numbers in it and translate it to like the setup. Okay, so there's the first step. All right, so how can you figure that out? You guys a head start there. So stay a step ahead of me. Give you guys a head start so you guys can beat me to the answer. All right. Is that what you guys got right there? Do you guys get that answer? Yeah. Right. All right. So it's pretty straightforward, right? So the fact that they were all stationary to start with, at least from this guy's point of view, right, they're all stationary. It means there was no momentum in the system. So when they push away from each other, that still has to be true. Right? Momentum's conserved. So we got one to the left and one to the right. I'll have this left speed. I'll call it a negative velocity. Right. So turn that. Okay. So the one going to the right is going to have a positive velocity. Boom, it comes out positive. Right? So you guys know AP likes more conceptual type questions. They might turn this into like two ice skaters, right? Change the story a little bit, but it's the same setup. They might say, what is the speed compared to the speed? Right? And maybe the fact that it's more massive means it's not going to be moving as fast, right? So you guys see it, that's also true, right? Right, next one, number 7. Got a small China bowl, has mass 0.45 kilograms. I think it's actually almost exactly 1 pound. Is sliding along a frictionless countertop at 1.28 meters per second. What is the kinetic energy of the bowl? Okay, let's pause and do that one real fast. Right, so here, give you guys a head start here. You guys calculate what is the kinetic energy? Right. Did you guys do this 1/2 mv squared? Whoops, gotta do a multiplier right here. Second, insert, multiply. 1/2 mv squared. That's what you guys did, right? Got 0.36 something joules. You guys got that? Okay. Now I'm gonna write that down. Okay. So we do that right here. I'll say kinetic energy initial equals 0.3686 joules. Now that's a lot of precision, but we'll just save some digits there. Okay. So we've got that many joules of kinetic energy. Okay. Subsequently, a server with perfect timing places a rice bowl of the same mass onto the bowl as it passes them. Okay? So maybe that's a practical way of saying like the mass doubles. Okay? So here this bowl is like sliding across the table. This guy like just drops a rice ball into it. Okay? What is the subsequent speed of the system, and what is the system's new kinetic energy? Okay? If you think this in terms of variables, this could be a good proportionality question. Like, what if they gave you no numbers and they just said like, how do the proportions of these things change? Okay. So if you just like place a ball of rice in a moving bowl and it effectively doubles the mass, what do you think is going to happen to the speed? Half as much, right? Right, because it has had the same momentum, right? Because you're not changing the momentum of the system, right? Just like placing a bowl of rice, okay? So you're doubling the mass, so you better have half the speed. Okay? What about the kinetic energy, though? Double the mass, half the speed. Here. Okay. So momentum is equal to mass times velocity. Okay. So if you double the mass, you have to have half the speed. So momentum is the same momentum. Okay. But kinetic energy, it's like 1/2 mv squared. Okay. So if you have double the mass and half the speed, what happens to the overall kinetic energy? Would be half, wouldn't it? Right? Because you have ×2 here, you have times a half times another half here because it's squared. So a factor of 2 times the factor of 1/2 being squared, that's overall half. So it's going to end up with the same momentum as it had before, same momentum, but half the kinetic energy. Wouldn't have to be, right? Let's try that out. Let's run the numbers. So we figured the speed had to be half, but the momentum had to, or the mass had to double, right? So the new mass is 0.90 kilograms because that's double the mass, right? That's the bolt plus the rice. Okay? And the V new, well, that has to be half as much. So it was 1.28. Let's add that 0.64. 64 meters per second. Okay. So let's see, what is the new kinetic energy? Do 1/2 mv squared. So 1/2 times 0.9 times 0.64 squared. Okay. I'm looking at 0.1843 joules, right? It should be half of what we started with. Okay. So let's see if that's true. Oh yeah, because we started with like 0.36. Now we're down to 0.18. That is half, isn't it? Okay. So you guys get it? So you guys can navigate proportions like that, right? Ooh, maybe you could make a more general case from this, right? So if two objects have the same momentum, what if you have like a bowling ball versus a ping pong ball, right? A bowling ball versus a ping pong ball, right? And they're both in motion. And they have the same momentum, Which one has more kinetic energy? Same momentum, right? What do you guys think about that? Which one has more kinetic energy? Let me see, show hands. How many guys think that the bowling ball has more kinetic energy? How many guys say the ping pong ball has more? Oh yeah, almost everybody. Yeah, you guys are right. Okay, ping pong ball has more kinetic energy for the same momentum. Okay, because yeah, whatever. Just in case you didn't follow that, okay? The ping pong ball has a lot less mass. Let's say it's a 10th of mass. That's not accurate, but let's just go run with it. Say a 10th of the mass. Well, it would have to have 10 times the speed to have the same momentum, right? Because your momentum is your mass times velocity. Right? So same factor is just reciprocal. Okay. Okay. But that whatever factor gets attached to the speed gets squared. So it counts a lot more. Okay. So the fact that those ping pong balls moving faster is going to ultimately give it more kinetic energy. You know, it has less mass. Okay. You guys get there? All right. Next one. Let's do one of these conceptual questions. Number 5. A ball of clay, mass m, is thrown with speed v against a brick wall. The clay sticks to the wall and stops. Is the principle of conservation of momentum violated in this example? Ooh, because it had some mass times velocity, right? And then after it sticks, it comes to rest. Where'd all the momentum go? Into the wall, right? Right. But wait, the wall's not moving though, right? Huh. So now where'd the momentum go? Into the earth. Right. So say I take a ball and I like throw it against that wall right there. Would that like change the rotation of the earth? Well, sort of yes, sort of no. The best answer is no, right? But here's why. Maybe like during the mechanics it like wobbles a little bit. Right? So if I let's say I have a ball, right? This could be like a ball, right? Right? And I throw it. Now when I throw it towards that wall, there's friction between my shoes and the floor. There's this whole like Newton's third law of force that's pushing me the opposite way, right? So maybe if I throw it that way, here, let me zoom out a little bit. Right? So if I throw this object that way and it starts flying through the air, right, I kick the entire Earth back the opposite direction. But then when this slams against the wall, right, now it all just equalizes, right? So it just kicks the Earth exactly the opposite way. So the change in the Earth spin, like after the whole process is over, doesn't change at all, right? All right, next one. Let's hit some of these problems. Ooh, got some impulse questions with some graphs. So your number 15. Force shown in the force versus time. Force versus time, right? You're already thinking momentum, impulse. Okay? Something to do with the area. Okay? X on a 1.5 kilogram object. Oh, they told you the mass of the object. Right? That might be relevant. Okay, this is one of these multi-parts. We got to figure out a bunch of things. What is the impulse of the force? Okay, so let's start with that. What is the impulse? All right. I'll solve it. You guys solve it. See if we get the same thing. All right. What'd you guys come up with for the impulse? Eight what? Newton seconds, 8 Newton seconds, right? So Newtons seconds, that'd be 8 Newton seconds, wouldn't it? Right? You could also say 8 kilogram meter per second, right? Newton second, kilogram meter per second, same thing, right? So 8 Newton seconds, usually impulses in Newton seconds. That's how they're quantified, right? Because I see 6 Newton seconds just from this rectangle, and I see another 1/2 base height for this triangle right here, right? Right. So there's another 2 right there, right? So 8 and 2 make, or sorry, 6 and 2 make 8. Part B, what is the final velocity of the object if it had initially been at rest? All right, who knows? How fast is it going? We figured it out. We figured it out? Here. So momentum is mass times velocity. Okay, got that. Okay. Now it started at rest, so the impulse would be the final momentum, right? Okay, so we're talking about 8 Newton seconds, you guys said, or you could call that 8 kilogram meter per second. This is the same thing. Right? It's the final momentum in this case. They said the object was 1.5 kilograms. Gonna have some V final. Right. Just divide over the mass, right? Divide the mass. When you do that, you should get V final is 5.33 meters per second, because I'm at velocity, meters per second. Kilograms cancels. Okay. Guys get there? Part C, the final velocity of the object if it is initially moving along the x-axis with the velocity of -2 meters per second. Ooh, I've seen AP ask this every once in a while. They give you an initial velocity that if you miss it, they're going to miss the question. Okay, so it's one of those details. Okay. So what if it had initially been moving at -2 meters per second? Can I just subtract 2 from this and call it 3.33? 3.33? I think I can do that, right? Okay, so that's maybe the shortcut way to get there, but maybe the longer way is to set up a whole like a momentum and impulse equation, right? It's a call this an open system. Momentum initial plus the impulse is equal to the final momentum, right? So now I'm doing it the long way, but the answer should just be 3.33 meters per second. So we started off with -2 meters per second for the speed, got 1.5 kilograms on the mass, okay, plus 8 Newton seconds of impulse equals 1.5 kilograms of mass times V final. Those V final hopefully is 3.33, but let's see if that's true. Okay. 1.5 times -2 plus 8, right, is 5 divided by 1.5. Yep, 3.33. 3.33 meters per second. Okay, there you go. 2 pass through the forest, they do the same thing. Number 16. Zoom in. Got another force versus time setup. Force magnitude F sub x acting in the x direction. I mean, this is all in one dimension, right? So all we're doing is just like pushing forward, right? pushing forward harder, 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 then at a constant rate really hard, and then less and less and less, but you're always just pushing forward, right? Right. It's all one dimension. Okay. On a 2 kilogram particle, so mass is 2 kilograms. Let's show this a little bit better. Right, find the impulse of the force. Right. Well, since we got a couple minutes, let's do the fast version. The impulse, that would just be the area of this trapezoid, wouldn't it? Right. If you like, I might break this down to this triangle plus this rectangle plus this triangle, and symmetrically looks like these two triangles are the same. So your force 8, 1 by force 4 is that 12? I think 12 Newton seconds. 12 Newton seconds, I think. The final velocity of the particle, if it had initially been at rest, right, and the final velocity. Oh, okay. Actually, that looks really similar to what we just did, right? Same idea. Let's take a look at this one. I think I signed this one to you guys for homework a long time back, and maybe ask you guys a quiz question. We got a 3 kilogram steel ball strikes a massive wall at 10 meters per second at an angle of 60 degrees to the plane of the wall. So this is 60 degrees right here. And it bounces off with the same speed at the same angle, right? So that's probably an elastic collision, right? Because it didn't lose any speed, right? So it didn't lose any kinetic energy. So elastic. The ball is in contact with the wall for a tiny fraction of a second, a fifth of a second, 0.2 seconds. What is the average force exerted by the wall on the ball? Okay. Do you need to do some trigonometry, sine, cosine type? Right? I'm thinking a sine component playing off this angle, because guys, does the wall apply a force on the ball parallel to the wall? No, it's only perpendicular. That would be a normal force, wouldn't it? Normal is always perpendicular, right? So I only care about the sine component, right? Right, because sine of this angle would be this direction. Okay. Right, it's going okay. And so also remember, when it rebounds, it goes from a positive to negative velocity, so you have to take that type difference. All right, so you guys have a great rest of your day.
I think I might have.